Okay, solubility equilibrium. Today we begin to apply all of the concepts we've learned in the unit so far. I've listed them here just as a quick refresher. The concept of dynamic equilibrium, the position of equilibrium, writing equations for K, constructing ice tables, which may or may not involve calculating Q, the reaction quotient, Le Chatelier's principle, and the calculations. So let's explore each of these then as it relates to solubility equilibrium. So that's a familiar concept already, the idea that the rate of dissociation of the solute into ions in solution equals the rate of recrystallization. And at that point, the observable macroscopic property that would remain constant is the size or mass of the excess undissolved solute. How would you describe the solution phase of this mixture? Your choices are unsaturated, saturated, or supersaturated. Okay, the correct answer is saturated. This solution here is a saturated solution. Saturated solutions contain the maximum amount of solute that can dissolve in a given amount of solvent at a particular temperature. And when equilibrium is reached, the solution contains the maximum amount of solute that it possibly can for that temperature. So that may be a very concentrated saturated solution, or in fact it may be a very dilute solution. It depends on the solubility of that solute. When we write an equilibrium equation for the solubility equilibrium, we have the solid in equilibrium with its aqueous ions. So over here, I'm showing you a solution that doesn't have any excess undissolved solute. How would you describe this solution? Unsaturated, saturated, or supersaturated? This solution is actually described as unsaturated. How do we know that it doesn't contain the maximum amount of solute? How do we know that it has less than the maximum amount of solute that can dissolve? How do we know the solution's not saturated? Well, I guess there's an outside chance it could be. If we were to add an extra crystal and that crystal did not dissolve, then for sure that solution was saturated. But typically, if we do not see excess solute, the assumption is that the solution is unsaturated. So if you've prepared the solution yourself and perhaps started with this mixture where you had excess undissolved solute and then filtered it to remove the solute, then you'd know for sure the solution you have left behind is saturated. Here we don't have any of that knowledge, so we would assume that the solution is unsaturated. Is this solution at equilibrium? Well, is a forward reaction occurring at the same rate as a reverse reaction, keeping a macroscopic property constant? And the answer is no. Only the forward reaction has occurred and there's no recrystallization happening. So the unsaturated solution is not at equilibrium. Now, how would you recognize a supersaturated solution? A supersaturated solution would take our saturated solution at equilibrium and increase the temperature. And if we increase the temperature, we will create the opportunity for more solute to dissolve. And the idea is to raise that temperature until all of that solute has dissolved. So at that point the solution is unsaturated, but it's at the higher temperature. And so then we cool this mixture back down to the original temperature, and if we can do that very carefully and have all the solute that was dissolved remain in solution, then we will have supersaturated the solution. Now, supersaturated solutions are very unstable. At this point, recrystallization would occur if the solution is disturbed, and we would begin to reform the excess undissolved solute. So only saturated solutions, this is the only equilibrium situation. Unsaturated solutions, only the forward reaction has occurred. Supersaturated solutions, the recrystallization occurs, and then once you have solute on the bottom, undissolved, that has recrystallized, then your equilibrium can establish again. And so unsaturated solutions do not reach equilibrium. Supersaturated solutions can reach a state of dynamic equilibrium. Okay, moving on. Let's write an expression for K. So look at your equation here of XY solid in equilibrium with the ions and write your equation for K. Hopefully you did not write a denominator because we ignore solids and liquids for the purpose of the equilibrium constant equation. And so really what we've ended up with is a product of the concentrations of the ions in that saturated solution. So we call this particular K equation and value KSP. So the SP standing for solubility product. And you can see that it in fact is a product. In other words, the answer when you multiply the concentrations of the ions. So K for solubility equilibriums has a special subscript SP. So KSP is called the solubility product constant. Okay, so let's interpret certain KSP values. Okay, for the first example, I'd like you to complete the solubility equilibrium equation for lead 2 chloride. So show the solid in equilibrium with its ions and balance the equation. Okay, now write an equation for KSP of PbCl2. So you'll notice that I raised the exponent for the chloride ion to 2 based on the balancing coefficient. On page 725 of your textbook, you'll find a KSP table, and if you look up the KSP of lead 2 chloride, you'll see it comes in at 1.2 times 10 to the negative 5. So what does that value of KSP tell you about the equilibrium position? So compare the amount of reactants and products in this equilibrium. So at times 10 to the negative 5, we definitely have a very low number of products, so a low concentration of ions in solution. So PbCl2 solid is only a slightly soluble salt, right? It has low concentrations of Pb2 positive and the chloride ion, and we know this because KSP is low. Now, what about calcium phosphate? Here's the calcium phosphate KSP. So let's go through and write an equation to describe the solubility equilibrium of calcium phosphate. Write out your KSP and then compare the solubility of calcium phosphate to the lead 2 chloride. Okay, so I wrote out the aqueous ions on the right side, making sure to have 3 calcium and 2 phosphate to balance the equation. In writing the equation for KSP, I used the coefficients as the exponents. You'll notice those here. Oops. You'll notice those here. And I omitted the solid because we exclude solids and liquids from the equations for K. After looking up the calcium phosphate KSP value, I noticed that this power is times 10 to the negative 33, which is certainly a lot smaller than times 10 to the negative 5. So lead 2 chloride was a slightly soluble salt. What would you say about the calcium phosphate? The fact that the product of these ions is so low, the answer when you multiply the concentration of the ions is so low, we would say that this is a very low solubility salt. So definitely less soluble than the lead 2 chloride. So neither of them are very soluble. They'll both form precipitates quite readily, but the calcium phosphate is even less soluble than the lead 2 chloride. And so we've interpreted the magnitude of K to compare the solubilities of these two salts. You will see on page 732 the solubility of ionic compounds, and this will be familiar from grade 11. Just to draw your attention to the fact that the top half of this table are the very soluble salts, and you'll find very few of these listed. In fact, there won't be any nitrates listed in the KSP table because those solutes are very soluble. But you will find carbonate compounds and phosphate compounds, hydroxide compounds. You will find calcium sulfate and barium sulfate. You'll find silver acetate and silver chloride. So, for example, there's silver chloride. And look at the value of KSP, times 10 to the negative 10. It's telling you it's a very low solubility salt. And that is consistent with the exception, right, to being very soluble, that the silver ion together with the chloride would form a precipitate. You'll also see carbonates. Carbonates, right, form slightly soluble salts. There is your KSP for silver carbonate, times 10 to the negative 12. You won't find sodium compounds in the KSP table. Why? Because they are very soluble, without exception. And so the K value would be very, very, very large. Okay, as a check of your understanding now of the comparison between lead 2 chloride and calcium phosphate, I'd like you to draw in each beaker the equilibrium system between each solid and their ions. So consider the components of the diagram, draw them too, and then check back with the video. Alright, so both diagrams show beakers with saturated solutions with excess undissolved solute. What's key is the different number of ions shown in the saturated solution. Neither are very concentrated, and yet because of the lower KSP of the calcium phosphate, at equilibrium there will be fewer ions of calcium and phosphate in solution compared to the lead ions and chloride ions in the first beaker. Okay, moving on. So now we're moving into calculations involving solubility equilibriums. Okay, so in example 1, I'm asking you to calculate the molar solubility of lead 2 chloride. Again, we're talking about a solubility equilibrium where we have a saturated solution of lead 2 chloride with excess undissolved solute. When you're asked for the molar solubility, you're really being asked for the concentration of that saturated solution. And so we're looking for the concentration of lead 2 chloride in the saturated solution. Let's begin with an ice table. So write your equilibrium system, again the solid in equilibrium with its ions, balance the equation, and then set up your ice table. Okay, so I have written the balanced equation for the ions and identified KSP. In order to complete the ice table, you need to imagine putting lead 2 chloride as a solid into water. What is the initial concentration of the lead and chloride ions in the distilled water? Hopefully you're thinking, well, there aren't any. That's right. Since the solid, lead 2 chloride, is not going to be part of our KSP equation, we can blank the solid all the way through the table. So our focus is the ions on the right side. Now, as we go to complete the change, we know that the change follows the mole ratio. And so we see a ratio here of 1 to 2, and that makes us think of plus 1x and plus 2x. So very familiar to the work we did in 7.5. Okay, as we know, I plus C equals E, and so we can add our I plus C in order to generate equilibrium expressions. So here we'll have x and 2x. As we continue, we write an equation for K. So Pb2 positive ion and the chloride ion squared, and go ahead and substitute our values for x. So x multiplied by 2x all squared. The KSP value can be substituted, 1.2 times 10 to the negative 5. Okay, and now we'll be able to isolate x. So don't forget to square the 2 at the same time as you are squaring x. And so we'll have x times 4x squared, which simplifies to 4x cubed. And then to isolate x, I'll be dividing by 4 on both sides, and then eventually taking the cubed root of the KSP divided by 4. Just to be clear on how I punch this into the calculator, I pressed the cubed root symbol, and then I opened brackets, 1.2 exp negative 5 divided by 4, close brackets, pressed equals. Okay, so x equals 0.014. You'll notice I did 2 sig figs here because my KSP had 2 sig figs. Okay, so in terms of determining the molar solubility, X is our molar solubility. And so we've determined then that the concentration of the lead-2 chloride in the saturated solution is 0.014 moles per liter. And if you're thinking that's a very low concentration, hopefully that makes sense because we know lead-2 chloride to be a low or slightly soluble salt. Okay, in example 2, I'm asking you to calculate the molar solubility of lead-2 chloride again, but this time in a 0.10 mole per liter solution of aluminum chloride. And so instead of dissolving or adding that lead-2 chloride to distilled water, you're now adding it to a solution of aluminum chloride that has a concentration of 0.10 moles per liter. So there are aluminum and chloride ions already present, and that will affect your initial concentrations in your ice table. So write the equilibrium system, the solubility equilibrium equation, and complete the ice table. Okay, so the lead-2 chloride equilibrium system is written. I set up the ice table, blank the solids. Now there's no lead ions in the solution to begin with, but certainly there are chloride ions. And so to figure out the initial concentration, of the chloride ions, I need to consider the solution of aluminum chloride. The concentration of the aluminum chloride is 0.10 moles per liter. You may recall from grade 11 that the concentration of the ions, it follows the mole ratio, and so the chloride ions here will be 3 times the concentration of that aluminum chloride, or 0.30 moles per liter. And so that's where I come up with my initial concentration of chloride ions. Now I'm just going to make that blue because in my ice table I want to be clear when I'm using the red coefficient. To complete the change row, I follow the mole ratio, so 1x here and 2x here, and so then that leaves me with x and 0.30 plus 2x as the equilibrium concentration of the chloride ion. So we continue as we did for the previous example. Construct our equation for KSP and substitute the value of KSP as well as our equilibrium concentration expressions and solve for x. So I've begun by substituting these algebraic expressions. Now, as you go to solve for x, I hope you're running through your head the 3 possible options. We can do our perfect squares. If that's not a possibility, then we'll check the approximation, falling back on the quadratic formula as our last option. So in checking perfect squares, the right side does have this binomial squared, and yet x is not, and so that won't work. Okay, let's check the approximation. So we're looking at the initial concentration, the 0.30, and dividing by that KSP value. Does that end up being greater than 100? Check it out, 0.30 divided by 1.2 EXP negative 5. You'll find that it most certainly is greater than 100, and so that 0.30 plus 2x can just be written as 0.30. And we're going to use that simplification to make the math of this problem take a lot less time. Look at the simplification that brings. Now we're literally just dividing by 0.30 squared on both sides, and we will have isolated x. So x is going to equal 1.2 exp negative 5 divided by the 0.3 squared. And so we finish with, as you might imagine, very small concentration molar solubility. So just to write our therefore statement, we'll say the molar solubility of the lead 2 chloride in the aluminum chloride solution is 1.3 times 10 to the negative 4 moles per liter. Okay, so how does the molar solubility of the lead 2 chloride in the aluminum chloride solution compare to the molar solubility of the lead 2 chloride in water? And you'll notice that our earlier value at 1.4 times 10 to the negative 2 was definitely greater than this solubility. And that's what we would expect if you think back to Le Chatelier's principle. If we have the PbCl2 solid in equilibrium with its ions, and we introduce an ion, like the chloride ion, from this aluminum chloride, if we apply Le Chatelier's principle, we're essentially increasing the chloride ion. So we would expect the system to respond to consume or try to decrease that chloride ion concentration, which in this case means the equilibrium is going to shift left. And as it does so, right, there will be fewer ions in the saturated solution. And if you have fewer ions in the saturated solution, that then reduces the concentration of those ions. Therefore, since that's what the molar solubility is, we've reduced the molar solubility. And we would say that that has decreased the solubility of this solute. So when you introduce an ion that's present in the solubility equilibrium, you reduce the solubility of the solute, and this is called the common ion effect. So we can apply Le Chatelier's principle here, and we can also prove that in our calculations above. Okay, a third example, perhaps more straightforward than the previous two, asks you to calculate the KSP of a saturated solution of strontium fluoride given these concentrations of ions. You'll notice I use the term respectively at the end, and that tells you that the order that the ions are listed in, corresponding concentrations follow in that order. So the strontium ion concentration is here and the fluoride ion concentration is here. So in this question we're asked to calculate KSP. That's the only time you can't look it up. You have to use the information from the question in order to calculate KSP. So build an ice table after writing your equation, substitute what you know, and calculate KSP. The concentrations of the strontium and fluoride ions that are provided are the concentrations in the saturated solution. Okay, so you'll see that I completed the ice table, but I directly plugged in the equilibrium concentrations of the strontium and fluoride that were provided, and then used those in the KSP equation. So was it necessary to construct an ice table here? No, it truly wasn't. If you recognize that the concentrations at equilibrium are the values that are plugged into your KSP, then you could have just written your equation, substituted, and computed the KSP. Okay, our last type of example. These are questions where you're asked, will a precipitate form? Remember calculating Q? Well, we're going to be calculating the ion product, and the ion product really is equal to Q. So it means we're going to take the expression for KSP and use concentrations not at equilibrium. When we compare the value of Q or IP to the KSP, if there were a greater concentration of ions than there are at equilibrium, the solution will be supersaturated. So if IP is greater than KSP and the solution is supersaturated, then recrystallization will occur and a precipitate will form. If IP, on the other hand, is less than KSP, then that solution is unsaturated. The reverse reaction cannot occur and a precipitate will not form. So manipulating these concentrations and volumes requires some background knowledge from grade 11 solution chemistry. So I'll just ask you to copy down the example and begin with the double displacement reaction to even figure out which precipitate is potentially forming. You'll need to check your solubility guidelines on page 732 and decide what the potential precipitate is. Okay, so we can see that calcium sulfate is the potential low solubility product here. And so we key in on the calcium sulfate for our equilibrium system. The question is, will a precipitate of calcium sulfate form? So we write our equilibrium system with our solid in equilibrium with the ions and set up our ice table. You can also look up the KSP of calcium sulfate. We'll be needing that later. Okay, so I looked up the KSP at 7.1 times 10 to the negative 5, set up my ice table, and blanked the solid. Now, in order to fill in the initial concentrations of the calcium and sulfate ions, I need to do a few solution calculations. So I've first sourced the calcium ion. It's coming from the 50 milliliters of calcium nitrate. So I've written now, you'll see down here, a dissociation equation for the calcium nitrate. The concentration of the calcium nitrate is 0.10 moles per liter. Following the mole ratio that I see in this equation, 1 to 1 to 2, I can come up with the concentration of the calcium ions. Now, could I calculate the concentration of the nitrate? Sure I could, but nitrate ions are not ions in the solubility equilibrium, so they're irrelevant for this question. So I follow the mole ratio of 1 to 1, and this is the concentration of calcium ions. Now, that's the concentration of calcium ions, so concentration of the concentrated solution, right, in my volume of 50 milliliters. But I'm looking for the concentration after mixing, which means when that has been diluted. We had 50 milliliters, and we combined that with another 75 milliliters of solution for a total of 125 milliliters. And so I'm looking to calculate the concentration of the calcium ions after mixing, which refers then to the concentration of the diluted solution. So I need to isolate CD, so I'll divide on both sides by VD, and I'm left with CD equals CCVC over VD. You'll notice that both volumes, units will cancel, therefore I'm going to leave those in milliliters. I don't need to bother converting those to liters. And so the volume of the concentrate was 50.0 milliliters, and I'm dividing by 125. And so we do 0.10 times the 50.0 divided by the 125, and we come up with 0.04 moles per liter. So that value is now the initial concentration of the calcium ion, so 0.04 milliliters. So I come back up to my ice table and fill in 0.04. I guess for 2 sig figs, I'll put another 0 there. Okay, now we repeat and do the same thing for the sulfate ion. So the sulfate ion came from the 75 mils of the sodium sulfate. And so I start with the sodium sulfate dissociation equation that dissociates into 2 sodium ions and 1 sulfate ion. The initial concentration there of the sodium sulfate was 0.20 moles per liter, and following the mole ratio, I'm interested in the sulfate, so I'll jump all the way over to the sulfate. Notice it's a 1-to-1 ratio. So that's the concentration before mixing when it's concentrated, and the volume at that point was 125 milliliters. I'm looking for the concentration of the solution after mixing, and the new volume is going to be again the sum of the two, so I'll end up with 125 mils. Sorry, I made a mistake here. This should have been the original 75 mils. Originally, we had 75 milliliters of the sodium sulfate, so that's the volume of the original concentrated solution. When we add the 75 plus the 50, we get the volume of the diluted solution. Okay, so in solving for CD, again I'll have CCVC over VD, and I'll have 0.20 times 75.0 over the 125.0. And so we do 0.20 times the 75 divided by the 125, which gives us 0.12 moles per liter. So that is now the initial concentration of the sulfate ion. So I come here to the 0.12 moles per liter. Okay, following the balancing coefficients, I can see that I'll have plus x here and plus 1x here, and so my algebraic expressions, 0.040 plus x, 0.012 plus x. Okay, now the point of determining whether the solution will precipitate or not, the decision there comes from calculating Q, or what we call the ion product, when it's a solubility equilibrium. So I follow the exact same formula as KSP, except I don't call it KSP because I'm substituting concentrations that are not at equilibrium. So 0.040 times 0.12 gives us, sorry, let me just double check this, gives us 0.0048 as our IP. Now how does IP compare to KSP? We've got 4.8 times 10 to the negative 3 here. We can see that the IP is greater than the KSP of 7.1 times 10 to the negative 5. So when IP is greater than KSP, that means that the solution is supersaturated, and therefore a precipitate will form. So the bulk of the work is done when you figure out the initial concentrations of the ions. Calculate IP from there, compared to KSP. If the solution is unsaturated, a precipitate will not form. If the solution is supersaturated, a precipitate will form.